I'll be talking about using geospatial for time-sensitive insights. I'll try to tie it in with the previous talk. It's no secret, we work very closely with Centera. We support them on their precision ag initiatives. So yeah, we provide specialized human-in-the-loop services for people who are developing computer vision algorithms or machine learning algorithms to solve problems in computer vision. Some of the spaces we work in: autonomous mobility, which is self-driving cars, self-flying drones, self-navigating trucks. We also do the work in geospatial technology, which is anything from geosat images to drone aerial imagery that has applications in agriculture as well. And we kind of dabble in a number of other areas. Medical AI is a growing field. Anywhere that AI is being used, our work comes in helpful. So some example use cases could be, using aerial devices to inspect, for example, utilities assets, to check for damage, to do inventory counts. Land use classification from aerial imagery is another big use case. Agriculture, the kind of stuff that Dimitris does, is also both aerial and from ground robots. We work with a number of customers in that space. And we also do a lot of asset classification and asset identification from the air. This can be anything from oil silos to railway assets to retail assets, retail chain assets, supply chain assets. So the basic problem that we solve is how to create the training data that can be used to train algorithms to detect and classify objects from the air. Specifically here, I want to talk about time-sensitive aspects. There are specific challenges to time-sensitive intelligence. There are sort of a spectrum of 3 use cases. You have non-time sensitive stuff where you have a few days or a few months to review the data and kind of come up with your analysis. That would be more of a batch-based kind of approach. Then you have sort of near real-time but not real-time time-sensitive intelligence. So that's typically monitoring algorithms in the field or customer experiences that don't need to be real-time, but maybe the customer is waiting for 20 or 30 minutes. Often you have seen when you try to onboard somewhere, there might be a 30-minute gap before you are approved for onboarding. That's a typical case which would be time-sensitive. And then, of course, we have real-time cases, for example, driving a car where there's really no scope for the human in the loop to intervene right there and then. The challenges of time-sensitive intelligence in ag tech, in precision ag, first of all, is the rapid spin-up of use cases. So as you go to different fields and different crops and different diseases, you have to spin up the algorithm to deal with a completely different type of data, which may have very little correlation. The kind of image processing and understanding you need from carrots may be completely different from corns. The use case may be disease, or it may be counting the crops, or it may be looking for weeds. It could be completely different. All of this requires specialized knowledge that resides in the head of agricultural scientists who work for our customers. And the trick here is, how do you extract that knowledge and kind of make it slightly generic, slightly narrow and deep, so that a generalist can learn the important aspects of this and contribute to this pipeline. Then you have the last mile problem. When you deploy an algorithm, so we're really seeing the phase of algorithms in both machine learning and AI going out of the lab and into the field, where your business critical process is actually running with the AI. And you have a last mile problem because most of these algorithms might succeed for 90% or 95% if you're lucky, but you can't afford to miss the other 5%. And so that also brings us to quality audits, which says that if, as Dimitris described, if data is coming in at such a rapid pace from the sensors everywhere, then how do you stay on top of it? How do you know that you're performing correctly, that you're not taking actions that might destroy healthy crops or missing unhealthy crop disease as they are forming? And how do you come in and audit that on an ongoing basis? If you don't look at your data for a month, the actions you took 1 month ago could have already caused a lot of destruction. So these are the key challenges in when you bring time sensitivity into it. And what we have worked with is a rapid methodology for machine and human fusion. Machine and human fusion means you don't try to solve the problem exclusively with AI. and you don't try to solve the problem exclusively with humans in the loop. You create a virtuous cycle of both, where the machine is trained to look at stuff at scale, but then the machine also knows when it's come across something that it doesn't know. And when you do that, you want the human expert to come in and kind of be the point of escalation, to be the point of quality audit. And as the machine evolves its algorithm, you also want the human monitoring it. So this is kind of an infinite loop that we project. From most technology companies, you will hear the model ops side, how to manage the machine learning models, how to manage the optimization of those models. But we believe that the data ops side is equally important and equally challenging. Just so you know, I will share this presentation after, so don't worry. I want to focus on the highlights. I'm not reading directly from the slides. You can come in at leisure afterwards and look at it. So, you know, if we look at the machine part of it and how to prep yourself, get ready for time-sensitive stuff. Dimitri's pointed out that, you know, one of the big challenges is with the data pipelines. So standardizing your data pipelines so that inside your company, inside your org, multiple use cases can be pushed through a pretty standard API to your machine learning and human pipeline. That's very important. That's one of the big accomplishments that Centera has done over the last couple of years, is really kind of making it easy for any team, any stakeholder in the company to start a machine learning project with leveraging the same data pipelines. You can bootstrap some models. One of the key challenges we face, since we are creating the training data, no model exists to help us to accelerate our work. So we have seen recently the evolution of models using techniques such as few-shot learning, which is a model that kind of gives you a crude first round with a few labeled data and helps you maybe remove 20 or 30% of the manual labeling burden. We've also seen techniques like transfer learning, where if you trained it on something else, then you can apply a few data from your current use case and try to get some better results rather than starting from scratch. So bootstrapping models is a very good idea to kind of shape your data and not unnecessarily label data. One of the things to know is that when you're developing these models, the confidence interval is as important or even more important than the accuracy. What that means is it doesn't matter if the model is inaccurate to start with. What really matters is the model is able to signal to you that it's not sure about a result versus when it's sure about a result. So if the model goes, I think this is a year of corn and I'm 98% sure about it, that's really helpful. If the model goes, I think this is a year of corn, but I'm only 60% sure about it, you might want to ask a human. That is also super helpful. So the confidence allows you to kind of cut off a threshold for when you trust the machine and when you escalate to a human. So in shaping your algorithms, this would be an area that's frequently important, because that's what allows you to you know, really know when you need extra help and when you can trust the model. And that's frequently the main question that comes up when you're providing the model out into the world. So finally, as I said, validating via audit pipeline and constantly doing that is very important. So your model's out in the field, you know, Dimitri's drones are running around doing things, and there's data streaming in. There are decisions being made by the algorithms every day. You really want to come in you want to come in and you want to audit that every day. You want to pick a random sample. You want to pick the low confidence samples. You want to see what's going wrong with the algorithm. You want to fix it pretty quickly. You want to detect underlying patterns. And this is all human insight. You have human auditors who are looking qualitatively and quantitatively at the decisions made by the model and kind of tweaking the model or making fundamental changes to the model, which can address these problems. So these are the key machine interventions. On the human interventions, which is what we specialize in, the first thing is, you know, this is a pretty specialized field. And what you really want is a dedicated team that you build up their expertise over time. Your agricultural scientist works with them consistently and transfers the knowledge in a standardized way each time. So whether it's corn or carrots or weeds or weed, you want a kind of a simple, straightforward methodology. And the most useful thing we have learned over time, I think, and which I think surprises some of our customers, is You create these methodologies and the labeling examples and instructions in order to break them fast. You learn more when things break than when they run routinely. And when they break is what I mean, that you detect edge cases, you find ambiguities, and you find sort of confusing situations that even the engineer did not anticipate. And the information contained in that edge case is 10x the information contained in the routine cases that work. So oftentimes you'll find algorithms get up to 60, 70, 80%, and then they really fail because of the last 20%. And that last mile problem is where humans are good at challenging the status quo. They look at a set of instructions and say, well, what if this happens? What if that happens? Or they see a data piece and they flag that to the developer and say, we came across this. You might want to consider this in developing your feature detection because this is ambiguous in your current feature set. So the edge case piece is often the barrier to adoption of AI. And the penalty is often disproportionate. This is very important, and this is why I come back to the confidence interval. Depending on the problem you're solving, you might say, hey, I don't mind spraying a few extra plants if they're healthy. But on the other hand, you might say, I don't want to destroy plants if they're not if they're healthy, but they were misclassified as being diseased. That could cause great economic loss. So depending on what you're trying to do, the penalty for false positives or false negatives can be disproportionate. And so you want to shape your methodology and what you want to focus on in the edge cases to minimize the penalty for wrong decisions in the field. This is very important in for example, in rare events. So if you're looking for potential risk for forest fire, it doesn't matter if you flag 10 or 12 innocent cases, but if you miss the one that's going to cause the fire, you can create a lot of problems. So as you can see, the penalty there is very disproportionate. And this is something you want to consider in designing your instructions and your models. So what are my takeaways? The first is you must co-design the machine plus human. I know most of us are engineers. We love the algorithms. We love to be in our Jupyter notebook and running stuff. But honestly speaking, that's just a small part of the problem. We're mostly configuring algorithms, and we really need to focus on the data. We need to focus on the data methodology, not just the data itself. Put a different way, if every little piece of this pipeline matters and deserves mindfulness, a mindful approach. Second, we emphasize repeatable pipelines and instructions. AI is challenging enough as it is. Every use case is different. Every algorithm has to be trained differently, even if you change your use case slightly. So you can help yourself by standardizing your backend pipelines, your data pipelines, your data formats, your instruction formats, your dashboards, your performance metrics. The more you can work with standardized environments there, the more space you can give yourself to customize the use cases. We've worked with customers that spin up a new aerial object identification use case every 2 weeks for a new customer. 1 week, it might be a customer who's looking at oil silos. Another week, it might be a customer who's looking at land use. A third week, they might be looking at solar panels on roofs for an insurance client. And the ability to kind of do that every 2 weeks depends on really process improvement. It's not so much the code as much as the thought process behind it. As I mentioned before, design to break is a great principle. Obviously, you want to fix it after, but mainly, disagreement is more information rich than agreement. We learn much more when there's a problem than we do when everything's routine. And finally, you must take care of the last mile. A number of AI initiatives are stuck in this space because they can't get past 80%, 85%, and the customer can't risk the other 15%. It's not a research situation. It's a live situation with an economic benefit and an economic penalty from their end customers. So the last mile, if it's mindfully designed with experts in the loop, if the pipeline escalates uncertain cases, if the audits are done properly, then you have the ability to take your AI to production and be a big superhero in your company. So I think those would be my inputs. Again, I think the models are necessary, but not sufficient, to use a mathematical term. And the data is necessary, but not sufficient. The infinity loop of both and constantly refining both of those is really the key to success in AI. Thank you.